Hello and welcome to this chapter on magnetism. There is an intricate relationship between electric current and magnetic field. So much so that wherever you have an electric current, you will have an accompanying magnetic field. So there is a series of 2 chapters, this being the first one, where we look at magnetic fields and the connection to electric currents. We will begin with looking at the Earth and its magnetism. This is called terrestrial magnetism. The Earth is a magnet. But if you have a compass or a magnet suspended freely where it can rotate, it's going to point along the red arrow shown. So the magnet will point along this line that is shown here, with the North Pole pointing down. As you can see, the North Pole is down. This is called the magnetic meridian. The magnetic meridian. But the important thing is to understand that it does not align perfectly with the geographic North and South poles. So you can see the geographic North Pole is away from the magnetic South Pole. Same here. So this is called the geographic meridian. There is an angle between the magnetic and the geographic meridian, which is actually called declination. Declination. Another thing to understand is that if a magnet is freely suspended, the North Pole of the magnet is actually pointing towards the South Pole of the Earth. You see that? Because opposite poles attract. So there is some history here. Magnetism was first observed in natural minerals like magnetite by the Chinese around 2000 BC. And then William Gilbert in the 1600s is the one who proposed that Earth itself is like a giant magnet. Then in the 19th century, Ørsted discovered that electric currents always generate magnetic fields, while Faraday showed that changing magnetic fields also produce currents. So we're going to look at that in another chapter called electromagnetic induction. So right away you have to know that an electric current produces a magnetic field, but a changing magnetic field induces an electric current. This in fact is the principle of electric motors and generators. We will get to that in that chapter. But magnetism has a lot of practical applications, using a compass for navigation, and then hard drives and tapes where data is stored magnetically. By the way, you know for sure that compact discs and DVDs, they store data in an optical format. It's not a magnetic storage. Okay? And then MRI machines, which stands for magnetic resonance imaging. Magnetic levitation trains, where the trains don't touch the rails and they are obviously very fast moving. So we have a lot of practical applications for magnetism. So this question I've already answered. If a compass needle points north, what does this suggest about the Earth's magnetic poles? The compass needle aligns with the Earth's magnetic field. Since it points towards the north geographic pole, that region is actually the magnetic South Pole, because opposite poles attract. I've already stated that. Now here is a question where you have a compass needle whose magnetic dipole moment is given as 3.0 times 10 raised to negative 2 ampere meter square. That's the magnetic dipole moment. And it's in a field of 5.0 times 10 to the negative 5 Tesla. Okay, so notice that the unit of magnetic field is Tesla, and the unit of magnetic dipole moment is ampere meter square. So all units of magnetism are specified using ampere, okay, because the standard unit is ampere. There is no basic unit for magnetism. Everything is in terms of ampere. We'll get to that in a minute. But here, what's the maximum torque it can experience? So this is similar to, look at this formula. This is similar to this formula that you studied, where if you have an electric dipole in an electric field, you have a torque acting on it, which is given by Pe sine theta, right? Similarly, you have mu B sine theta, where mu is the magnetic dipole moment and B is the symbol for magnetic field, comparable to electric dipole moment and electric field. Do you see the correlation there? And maximum torque acts when the angle is 90. And so this is a cross product, actually. It's a cross product of mu and B. That's why you have the sine theta. And since mu and B are given here, all you got to do is multiply them and you get the answer in Newton meter, which is the torque. Next up, we come to one of the more important formulas, where we have the force acting on a charged particle moving in a magnetic field. So here you have a constant magnetic field of strength B Tesla, and you have a particle of charge Q moving through that magnetic field with a velocity. If the charged particle is moving parallel to the magnetic field, there is no force acting on it. If it's moving perpendicular to the magnetic field, maximum force acts on it. Now, since this is a cross product, you would understand there are three vectors in play here: velocity, strength of the magnetic field, and force. They are mutually perpendicular to each other. Now, to find the directions between them, we use what is called the right-hand rule. There are two right-hand rules. This is the first right-hand rule. And, of course, it's a right-hand rule, so you have to use your right hand, and according to this rule, if the fingers, if you stretch it and the fingers first point towards the velocity of a positive charged particle. So we're talking about a positive particle moving in the direction from the foot of the fingers to the nails, to the tip. And if the palm represents the direction of the magnetic field, you can see the palm represents the direction of the magnetic field, the uncurled fingers represent the direction of velocity, then the force on that charged particle, that positively charged particle, is given by the thumb. So that's important. You're going to have conceptual questions based on this. But do remember that if it's a negative charged particle, you can apply the same rule, but just know that the force will be acting exactly opposite. So that's the right-hand rule. I hope that's clear. So here you have the magnitude of the force acting on that charged particle, and this gives you the direction of the force acting on it. There is something about magnetic field lines. We'll talk about that in the next one. Here's a question. A straight wire carries current upward. What's the direction of the magnetic field around it? So here is where you use the second right-hand rule. Okay, I'm going to show it to you. So it's a different case. Here you're talking about a current carrying conductor, and it sets up a magnetic field around it. As you can see, on the right side, you see the current flowing through the straight conductor, and the magnetic field is in the form of concentric circles, meaning all having the same center. But to find the direction of the magnetic field, now we have to use the right-hand rule again, but this time you have to hold, or imagine that you're holding the conductor in your right hand with the thumb pointing in the direction of current. If so, the curled fingers will give you the direction of the magnetic field. So that's right-hand rule number 2. Now that's a 3D picture, but if you are asked to find what's the magnetic field at this point to the left of the conductor, you have to say it's perpendicular to this page and out of it. This is represented by a dot. So whenever you see a magnetic field represented by a dot, that means it's coming out of the page. And on this side, on the right side, obviously it's going into, see that? Here it's going into the page. That's represented by an X. It's like you're seeing the back of an arrow. Here you're seeing the tip of the arrow. This again is very important as conceptual questions. Okay, I hope that makes sense. Here is a very simple problem. A proton moves perpendicular to a magnetic field of 0.01 Tesla at 2.0 times 10 raised to 6 meter per second. What's the magnetic force? Because it's perpendicular, sine 90 is 1, so maximum force given by QVB acts on it. Proton has the same charge as the electron, and then you have the velocity, you have this magnetic field in Tesla, all proper units, you multiply them, you get that tiny force acting on the proton. Now, going back to magnetic field lines, I wanted to show you the picture of magnetic field lines here. So this is a magnet, a bar magnet, and you can see that magnetic lines are always from north to south outside the magnet and from south to north inside the magnet. So magnetic field lines are closed. See, I said that here. That's a complete different scenario from electric field lines, because electric field lines are not closed. If you have a positive and a negative charge, electric field lines just start from positive and end on negative. It doesn't circle back. See, that doesn't happen. So electric field lines are open while magnetic field lines are closed. This is going to be important as we move through the chapters. And also, if you want to find the direction of the magnetic field at any point, just draw a tangent to the line at that point. So if you want the direction of the magnetic field at P is along this direction, while at Q it is along the tangent drawn to the field at that point. And if the magnetic lines are closer, it shows a stronger magnetic field, while if the lines are further apart, it is a weak magnetic field. Alright, so here you see two magnets. You're just seeing the north pole of one and the south pole of the other, and this is how the field is going to be. But if you have the north and the north, then you're going to see the field lines repel. So it's like pushing back, which means you have an area where you have no magnetic field, this area. So that's called the null point or neutral point, so where you have no magnetic fields. Okay, so that is what was given here. Magnetic field lines are continuous loops and so on. I've just said that. And field lines cannot cross each other. They don't cross each other. They won't intersect. As you can see, this was true also in the case of electric field lines. Now here is a question that I wanted to include here, where you see how matrices can be used to calculate the force on an electron whose velocity is given. Velocity is 7.0 I minus 6.0 J times 10 raised to 4 meter per second. The magnetic field through which it is moving is also given in vector notation, and you're asked to find the magnitude and direction of the force on the electron. So here we know the formula is Q V cross B, and we're going to use matrices to find the cross product. How do you do that? So you have the IJK, but the order is important. So first take the components of velocity. You can see 7.0 times 10 raised to 4, that's for I, and that's J. There's no K, so it's 0. Next, for the magnetic field, same thing. You put down the components, and then this you have to know. I'm not going to go through it, but you have to know to find the value of the coefficient of I. You just ignore that and go this times this minus this times this, because I is J cross K. Alright, J cross K gives you I. So you should have studied this in UP1, so that's why I'm not taking too much time on this. But anyways, since both are multiplied to 0, it vanishes. That's why you don't have an I. Now to get the value for J, similarly, you just isolate that and go this times this. Once again, you're going to get 0. That's why you don't have any coefficients for I and J. But when it comes to K, you isolate this and then go this times this, which is what I've written here, minus this times this. You see the minus there, and then I have it done. And then do the math, and finally you will get the answer. Once you get this multiplied with this, of course, and you get the answer as so many newtons along the K unit vector, or K cap. I have included another question which you can look at. It's the same process, but here what we have to find is the electron's velocity. So the same formula, the force is given, so we'll go with this is equal to, look at the same thing, and since the magnetic field only has the K, you just put it as this. See, I've just given a general formula. It doesn't have an I and a J, so it's 0. And then you do it, and after you do it, you can put the coefficients of like terms equal to each other. So the coefficient of I here is that, and the coefficient of I on this side is that. That's why I have put f sub x is equal to that. And then from there you can rearrange, make the subject b sub y, and then get the answer. Same thing is done. You take the coefficient of j here, take the coefficient of j here, put them equal to each other, which is done again. Of course, you know that the two negatives make a positive, so that's why it's positive. And then rearrange, substitute, and you get the components of the velocity, both the y and the x. Finally, we know that that is the velocity. So this is also important for the exam, and that's why I just put it there. You can pause and take another closer look at this. Now, here is one of the consequences of a force acting on a charged particle in a magnetic field. Study the diagram. You see that the x's here represent a magnetic field perpendicular to the screen and into it. And then you have a negatively charged particle that's moving from left to right. So the velocity is from left to right. According to the right-hand rule, as soon as the particle enters this region where you have the magnetic field, a force acts on it. Remember that force being a negative particle, it will be downwards. So that's what is shown here. So as soon as the force acts on that particle, it bends. So instead of moving in a straight line, now it's moving slightly down because of that force. Now, as it bends, the force also has to be always perpendicular to the velocity. I hope you get that, because The force is along the radius and the velocity is tangential. So that means it bends again. And when it reaches here, you can see that its velocity is that way. Now the force is always towards the center. So it keeps on bending until finally it completes a complete circle. Now this is true as long as the magnetic field is set up in a wide enough area. Okay? So now it's up to us to find out the radius of this circular path. Whenever we talk about circular motion, we should know that there is the centripetal force acting on it from UP1. The centripetal force, mass times velocity squared by radius, see that, is equal to QVB, because this is maximum. The angle is always 90, so it's maximum. The centripetal force in this case is the magnetic force. That's why I've put them equal to each other. And then when you do the math and rearrange, you get this very important formula for the radius. It shows that the radius depends on the velocity. So if the particle is moving faster, it's compelled to go around in a bigger path, obviously. It also depends on the mass of the particle and the charge, or rather, the ratio of the charge to the mass or the mass to the charge. Obviously, it depends on the magnetic field. Now, how does it depend on the magnetic field? A strong magnetic field is going to make it move around in a smaller circle because it's in the denominator. Okay, so that formula is important and you can be asked to do problems, very simple. And then because it's circulating, it's going to make a certain number of rotations per second, and that's called the frequency. Right, we know that F is omega by 2 pi, because omega is 2 pi times F. And so omega is velocity by radius, and I've substituted that. And then when you substitute the value of R as m times velocity by QB, the velocity is going to cancel out and you get this, okay, this formula. So that's the formula for frequency. It's a very interesting formula because the frequency is independent of the velocity. It's independent, and it's independent of the radius. So how many times it circulates in a second only depends on its charge by mass ratio and the strength of the magnetic field. Note that as a conceptual question. Now, there are so many applications of this. We're going to look at two applications as we move on. One is the cyclotron, and then the second we're going to look at is mass spectrometry. Okay, but there are other applications. Here's a simple problem. A proton moves at that velocity, perpendicular to that field. What's the radius? Simple substitution. Mass times velocity by QB. That's the mass of the proton. It'll be given velocity, charge, B, and you get the radius. Another one, here it's not entering perpendicular. An electron enters at 45 degrees. What's the pitch? So let's go on to see what that means. Okay, look at this. If the particle does not enter perpendicular to the magnetic field, the first thing we have to do is break up the velocity into its components. You have the perpendicular component and the parallel component, meaning parallel to the magnetic field, perpendicular to the magnetic field. This component is going to make it move in a circular path. The perpendicular component makes it move in a circular path, while the parallel component of the velocity makes it move forward. So if you combine these two motions, you're going to get what's called a helix. Okay? And the pitch of the helix means the distance between consecutive circles. So to calculate the pitch of the helix, first we have to find the time period. You all know that time period is the reciprocal of frequency. time period is 1 by frequency. So that's why the formula for frequency is inverted here. So once you get the time period, that's the time taken for one circular motion, one oscillation. You just multiply that with the parallel component to find the pitch of the helix. So that is what is done in this question. So first, the parallel component is velocity cosine of the angle, and then you just multiply that component with the time period. I forgot to put the numbers in, so you can do that. And there are similar problems here, very similar. What's the radius? And then here's something that we discussed before. What's the force direction for a positive charge eastward in a field pointing up? Now use your right hand, and this is a good chance for you to try to figure out the direction. It's a positive charge, so you can safely follow the direction of the thumb. The charge is moving eastward, so you have to hold your fingers of the right hand stretched in the east direction, and you have to hold the palm pointing up because the palm represents the field. So if you do that correctly with the fingers from your left to right, because that's the east to your right side, and the palm pointing up, then surely the thumb is pointing towards you, which is out of the page. I hope you get that. Okay. Why is the force zero when velocity is parallel to magnetic field? Because the cross product is zero. Sine zero is zero. That's why. I worked out a problem here which uses those two formulas. The electron, the strength of the magnetic field, but it's entering at 45 degrees. And yeah, that's a similar question as before. You have to find the radius and pitch. Speed is given, or velocity is given. First thing, you break up the velocity into its components. So you have to find the radius using the perpendicular component of the velocity. You have it here. It's a velocity sine 45, which is the perpendicular component. You get the radius. And then you can find the time period using this formula. And to find the pitch, take the horizontal component of the velocity, which is cosine 45. Now, incidentally, sine 45 and cosine 45 are equal, so it doesn't make a difference in this case, but if the angle was anything other than 45, it's going to make a difference. Anyways, take this velocity component, which is parallel, and multiply it with the time period, which you can see 2 pi m by qb, and you would get the pitch of the helical path. All right, moving on. Magnetic fields produced by electric currents. We already did take a look at how to find the direction of the magnetic field using the second right-hand rule. So I'm not going there again. Now we got to find out how much the magnetic field is. Obviously, if it's closer to the conductor, then the magnetic field is going to be stronger. Why? Because you see the lines are closer when you're nearer the conductor. But to find the formula, you have to, here we are actually finding the formula for force acting. Remember that, okay? Force acting on this current carrying conductor kept in a magnetic field. All right, let me slow down. So if you have a current carrying conductor all by itself, it's going to produce its own magnetic field around it, right? Now let's assume that this current carrying conductor is kept in another magnetic field. Now the two magnetic fields are going to interact. What do I mean by two magnetic fields? One is the magnetic field in which the conductor is situated. The second is the magnetic field produced by the current flowing through the conductor. Now, when these two magnetic fields interact, a force is going to act on this conductor. And that's the principle of an electric motor right there. We're trying to find what's the force on this conductor. To do that, you have to remember that the current through a conductor is given by this formula. Let me explain the terms. Current, this is the number of electrons in 1 meter cube. This is the area of cross-section of the conductor. This is the conductor we're looking at. This is the area of cross-section. This is the charge of the electron. This is what's called the drift velocity, which is the velocity of the electrons. Okay? So the number of electrons in 1 meter cube, the area of cross-section, the charge of the electron, and the velocity of the electron determines the current. The magnetic force on any single charge carrier is given by Q, P cross B. Now instead of Q, we are just using E, which is the charge of the electron. No difference here. Okay? F is Q, velocity cross B. Now that's the force on a single electron. To find the force on the entire conductor, we have to multiply this with the number of electrons in that conductor. How many electrons do we have in 1 meter cube? These many, N. That's in 1 meter cube. So if we find the volume of the conductor, which is area times the length, right? Area of cross-section times the length gives you the volume. So if you got the volume here, and then if you multiply it with the number in 1 meter cube, this gives you the total charge carriers in the entire conductor. So you multiply that with this, you get the total force. That's what has been done. This is the force on a single electron, and then you multiply it with the number of electrons to get the total force. Okay. So now look at this. I have rearranged this. I've picked these together. You know why I did that? Because I know that these together is called I. See, I showed you that in the beginning. That's called I. So it's I dl cross B. So we got a new formula. The force acting on a small conductor of length dl carrying a current I placed in a magnetic field of strength B is given by I dl cross B. Again, it's a cross product. That means maximum force is going to act when it's situated perpendicular to the magnetic field. Okay. So generally, if you want the whole force, it's instead of dF, I've changed it to force, and instead of dl, I've changed it to this. So what's important is to know the length of the conductor, the magnetic field in which it is situated, the current through it, and you get the force. So a bigger current is going to activate a bigger force. All right, you're coming to the idea of a motor. So if a motor carries a bigger current, it's going to rotate faster. We'll get to that in a minute. Okay. So this magnetic force on current carrying conductors has a lot of applications in electric motors, loudspeakers, and so on. Okay. And here are some simple examples where you just multiply the two to find the maximum force. Okay. And then you can find the direction once again using the same right-hand rule number 1. So I've done 2 problems there. Take a close look at that. It's simply the multiplication of these quantities. This is interesting. What happens if the wire is parallel to B? Well, no force acts on it. You should remember that. And this is another chance for you to look at this conceptual question. What's the direction of force on a vertical wire with upward current in a westward B field? Okay. So the palm represents the magnetic field. So now take your right hand and the palm should be pointing from your right to the left. Good? With the current, upward current. Okay, so now you have to turn your right hand, palm, so that the palm is from your right to left, but your fingers are upward. Okay? fingers are upward. So the thumb is now surely pointing towards you, which is the south. I hope you get that. Okay. Another thing you should have noticed here, if you're paying attention, which I hope you are, is that the direction of current is always taken as the direction of flow of positive charges. Okay? So that's why when we said, when the question said the current is upward, we had no hesitation in saying, okay, so that means that's the direction in which the positive charge is moving, and so the fingers are pointing up. Right. Now, this question I had asked on an exam, and the results were very bad, so I've shown it here. So it says, suppose a straight copper wire whose diameter is given could float horizontally in air. That would be wonderful. Because of the force due to the Earth's magnetic field, which is horizontal, we're assuming it's horizontal, it's perpendicular to the wire, and of magnitude that much, what current would the wire carry? It's a very interesting thing. If you could have a current carrying conductor just floating horizontally in air, that would be great. Well, this is hypothetical. It's not going to happen. You know why? Because in order for it to float, it should balance its weight. The weight, mg, should be balanced by the force due to the current. So you can see it from the diagram. And then when you make I the subject, you get all this. Another thing I've done is mass. Mass is what? Volume times density. So this is the volume, pi r squared times h, or the length. Volume times density gives mass. And so change millimeter into meter, which I've done. Substitute all those numbers and calculate, you get, wow, why did this go off? It's like 1,400 ampere. All right, let me try it. It's 1,400 ampere. Now, that's not practical because such a large current would produce a lot of heat in the wire and would probably melt it. So it's not going to happen in life, but that's a hypothetical question, okay? By the by, the heat produced depends on the square of the current. So such a large current, you're going to get a lot of heat, and that's why it's probably going to melt. Okay, so here's the electric motor. I'm not going to go into details, and I'm going to go really fast. So what you have is a coil. In this case, it's a rectangular coil situated in a magnetic field. So you can see that usually this magnet is a U-shaped magnet. So the magnet is actually, okay, let me just draw with this. The magnet is kept like that. See, it's U-shaped, and that's why you see the South Pole here, you see the North Pole here. This is one of the strongest forms of a magnet, and that's why it's used. And also, the pole faces are not flat, it's arc-shaped in such a way that the two arcs form a part of a circle. The idea is to have a radial magnetic field here. So that means if I were to draw the magnetic field would be along the radius. Oh, that's not right. Let me try again. Obviously, drawing with the mouse is difficult. Okay, so the magnetic field would be like that. It's along the radius at every point. Now, why is that important? Why is that necessary? Because when the coil rotates, at each and every point, two things happen. The length of the coil is always going to be perpendicular to the magnetic field, while the width of the coil is going to be parallel to the magnetic field. Got that? Now that's important because since these two, or even on this side you would have one, there would be no force acting on anything parallel. So no force on this side. At the same time, you have maximum force on this side and this side, right? But since the current flowing through those two sides are in opposite directions, you can see that, the current has to rotate back, the current in the opposite lengths are in opposite directions, which means that the force acting will also be opposite, as you can see. That creates a torque, which makes it rotate. Now the arrangement has what's called a split ring, touching against brushes, metal, and this is carbon usually. Now the idea is that even when this rotates, we need to have a contact all the time for the current to flow. I mean, otherwise these cables will get entangled. I suppose you know that. So that's why that's given. And you see that the coil begins to rotate. So that's the simple principle of a DC electric motor. As long as you send a current, look, through this thing, as long as a current is flowing through this and completing the path, this will keep spinning. That's an DC electric motor. And to find the maximum torque acting, remember this formula, NIAB sine theta. Please write that down. And we get that easily using, the ILB, which is the force acting on each length. And torque is this times the distance, which is the width of the coil. And the length times the width, that's how you get the area, okay? And N is the number of turns. Now this is shown as a single loop, but if you were to have a coil which has a number of turns, then you have to multiply with the number of turns to get the total torque acting on the entire thing. So that's how you get that formula. Now this part, NIA, well, NIA sounds familiar, right? That's called the magnetic dipole moment, mu. We had introduced that before, so this is called mu. So once again, torque is mu cross B, or mu B sine theta. Applications in electric motors, galvanometers, which are current detectors. We'll come to that again, MRI and rotational sensors. Okay, so here are some straight problems. Loop, length and width given, current given, magnetic field at 30 degrees, what's the torque, straight substitution. Because it's a loop, n is 1, that's why there's no n there. IAB sine theta. What about if it's a circular loop? Well, the only difference is to find the area you use pi r squared, right? Check if the calculations are correct. So pi r squared is the area, and then use the same formulas. You got the area, now you got to multiply with the current B, and you get it. All right, another one at 60 degrees. What if the loop is parallel to the field? Well, then the torque is 0. What are the factors that affect the magnetic dipole moment? Of course, area, current, number of turns. Because dipole moment is NIA. NIA. Now, these diagrams just show what I was explaining before, that the torque acts in opposite directions and creates rotation. And this question is once again similar, so I'm not going to take time to read all that. It's just an application of that formula. Torque is NIAB sine theta. And if it says maximum torque, automatically theta is 90, so you get the magnetic field. Okay, you can pause and take time to look at it if need be, but otherwise I got to be moving on. And we come to almost last part. There's one more after this, but this is interesting. Mass spectrometer. So mass spectrometers are used for many purposes, but one of the main things is to detect isotopes. You all know what an isotope is? Isotopes are elements of the same material, but they have different mass numbers. Now, mass number is the total number of protons and neutrons. So the number of electrons are the same. So, for example, you have oxygen 16 and oxygen 17. The atomic number is 8 for oxygen. But 16, 17 means the mass numbers are different. So how do you find how many isotopes a material has? It's using the mass spectrometer. There are many types of mass spectrometers. This is called the Bain-Bridge. Look it up. BAIN bridge. Bain-Bridge, that's the name of the scientist, spectrometer. It's here, the Bain-Bridge mass spectrometer or spectrograph. Okay. It has two parts. The first part is called the velocity selector. This part is called the velocity selector. Let me explain. So you have a source from which all of the isotopes of this material is coming in through two slits. As you can see, these are passing through two slits. So you confine them into a narrow beam. But they then have to pass through an area where you have both an electric field and a magnetic field. But these fields are set up perpendicular to each other. Alright, so you see that the electric field is from right to left, while the magnetic field is, what does the X show? Into the plane of the paper. So they are perpendicular to each other. So when a charged particle passes in this area, the force acting due to these two fields are going to be opposite in direction. So the magnetic field is going to try to push it in one direction, the electric field is going to try to move it in another direction. So what's going to happen is, if the two forces are unbalanced, the particle is going to either go this way, hit this part, and not proceed into the next space. See that? But if the forces are equal, then the net force acting on the charged particle is zero. Those are the only particles that will go through straight. And that's what we want. So what did I say? The two forces are equal. What are the two forces? The electric force is given by Q times E. You may remember that. Q times E. And the magnetic force is given by QVB because it's maximum, right? I've written it down somewhere here. All right. Magnetic force, where is it? All right. And if they're equal to each other, then you know the Q's cancel out and you get this velocity. Now this is why it's called a velocity selector. So whatever the electric field is, whatever the magnetic field is, their ratio determines the velocity of those particles that will go through. So we are sure, one thing, we are sure that only particles that have a certain velocity enter the second space. And what do we have in the second space? We have another magnetic field also set up perpendicular to the screen and into it. Now, there's no electric field here. So what happens is, when these particles enter this magnetic field, you may remember that they are compelled to go around in a circular path or a semicircular path because we have a particle detector here which can be moved. So to catch the particles moving in different radii. So if you move this here, then you're getting particles that move at a lower radius. You move it here, you're getting those that move at a higher radius. So the idea is, I'm going to show you with the formula that the radius of the circular path depends on the mass of these particles. And of course they're charged, but they all have the same charge because they have the same number of protons, but their masses are different. So we're going to find particles of different radii, and by measuring the radius, we can actually calculate the mass of these particles. Now, to do that formula, we have to remember that the centripetal force is now given by QVB prime, which is the new magnetic field, okay? And then we know this formula, so radius depends on the mass and the charge. And I've just rearranged it. But before we do that, remember that we can substitute for the velocity using this. So I've done that. Velocity is E by B. And then finally you end up with this formula from which I have made the charge by mass ratio the subject. And you get this. What does it show? It shows that smaller the radius, bigger the charge by mass ratio. But by knowing these numbers, we can actually calculate the charge by mass ratio of the isotopes or the charged particles. So that is very important. Isotope mass measurement, atomic mass determination, nuclear physics research. So all these are the applications of the spectrograph. All right, that brings us to the last one. It's called the cyclotron. It is a particle accelerator. Now, where do we use this? We use this in nuclear fission. What is nuclear fission? Where you have a nucleus hit by a fast-moving particle, and it splits into 2 or 3 parts. That's nuclear fission. So we need a fast-moving particle. And that fast-moving particle is produced in a cyclotron. So that's why it's called a particle accelerator. There are many types of particle accelerators. This is just one, I think, invented by Lawrence and Livingston. So let me show you the construction. It basically has 2 hemispherical hollow cabins. You can see the D1, D2 because they have the shape of Ds. It's hollow inside, and it's these Ds are kept in a magnetic field. You see the South Pole and the North Pole of the magnet, and also you have a high frequency voltage source here. Now, let's stop there. This is not DC, this is AC. What does that mean? That means that at one instance, D1 becomes positive, D2 becomes negative, and so on. And then D2 becomes positive. It keeps switching. And that happens at a very high frequency. Okay? We'll do AC as the last chapter in electricity, but you just need to know this, that D1, D2 keep switching polarities. They become alternatively positive and negative. Now, that being the case, let's assume that a positively charged particle comes out from here. This is a source that produces particles. So if it's positive, it's going to get attracted towards D, the D, which is negative. So assuming that, now, according to this diagram, D2 is negative. So it's going to get attracted here. But do also remember that once it enters the D, there's no electric field. Do you remember that? There's no electric field inside a charged conductor. So there's no electric field, but there's a magnetic field. What does the magnetic field do? The magnetic field compels it to move around in a semicircular path, and the frequency is adjusted in such a way that by the time this particle reaches the gap, D1 becomes negative. So it's again attracted towards that, and then goes around a bigger circle. Why? Because its velocity is increasing. So what the electric field is doing is it's speeding up the charged particle. What's the magnetic field doing? It's keeping it going around in a circular path of bigger and bigger radius. So you can see that here. It comes out, goes down, keeps on going around in bigger radii, and then finally it comes out. So for that, you have another electric potential here just deflected out. And here you have the nucleus waiting, which gets hit and splits into 2 or 3 parts. So that's the fastest I've explained this, but I hope you can understand what I was trying to say. So the electric and magnetic field together produces a fast-moving particle. Okay, so read that. And then all of the formulas that we used before are applicable here. The radius formula and everything. Well, what we need here is just to find the maximum kinetic energy of those particles that come out. Now, kinetic energy is 1/2 mass velocity squared. All we got to do is go back a few pages and look at what we got for velocity. You would see that we get QBR by 2m. Okay, let's go back. Velocity. If you make velocity the subject, ooh, that's going to be a big journey. Okay, let's go. Velocity the subject. Where was that? Right, almost there. If you make velocity the subject, okay, you will get QBR divided by m. Right? If you make velocity the subject, QBR divided by m. So that's what we have used here to find the maximum kinetic energy. Okay. QBR by m. And now the 2 from here, and because it's squared, that's why we have to square everything, and one of the masses gets cancelled. Okay, so remember that. And here is a formula, a problem, where you have to calculate the maximum kinetic energy, and of course, it's just straight substitution of whatever is given. The charge, the magnetic field, the radius, 2 times the mass of the particle. This is a proton. I can see that. Protons, okay, because I recognize the mass given there. So you get that, and it's such a small kinetic energy. Now, electron volts, you remember that? Electron volts, energy is usually expressed in electron volts, and 1 electron volt is 1.6 times 10 to the negative 19 joules. So once you get it in joules, to change it into electron volt, you just divide by that number. And if you want it in mega electron volts, then you go 10 raised to 6, divide that by that number as well. So you get 4.3 mega electron volts. And that brings us to the end of this very important chapter. I hope you've been paying attention. I hope you've been listening. Because once you listen to this and understand the concepts, solving problems become easy. And remember, there'll be a lot of conceptual questions on the exams, which is where your physics is being tested, whether you understood. So take time and do your best. Thank you. We'll see you on the next one.